In today's notes, we're going to be looking at the results of the tumble buggy experiment, which was a little toy car that went at a constant velocity. The point of this experiment was to obtain the constant velocity model, which was a graph of constant velocity, and then an equation for constant velocity with which we can apply to other situations. The purpose was to then graphically model the relationship between time and distance, and then using that graph, we could then create a mathematical model of the relationship between time and distance for the tumble buggy, which was an object moving at a constant speed. So we start off by collecting data, with which we get graphs. So I'm going to put a copy of our overall nice polished version of the graphical model for constant velocity. I'm going to call it constant velocity as opposed to constant speed. In class, we discussed that we'd rather have time on the x-axis in seconds and distance on the y-axis. From here on out, I'm not going to use the letter D. I'm going to use the letter X for position, meaning the location of it on a tape measure, what meter mark we're at on the tape measure. So this is in meters instead of centimeters. Again, we're going to use meters for distance, and then the variable will be X for the position along a tape measure that measures meters. We found this to have a straight line relationship. I don't need to worry about the max and min values. We don't have to worry about that for right now because this is just showing what we need to have. But I do want to say that X is position, and that's in meters. And this time is lowercase t. And the standard units that we're going to always use to measure this will be in seconds. Okay, and this was linear for constant velocity. The other thing then we had was the mathematical model. And this is for constant velocity. This came from our graph. It's the linear equation, sort of reformatted. So instead of like y-axis, we're actually going to use x. Very confusing, I know. Instead of the x-axis, we're going to use t for time. So we're going to say that this is going to be x for position. I'll make sure that that's not confused, is equal to, and I'm going to pretend that the slope was 0.5. Put parentheses around this. I'm going to leave a little bit of space because we're going to put units in here in a second. This is times t for time, plus, and the y-intercept, we're going to put 0. I'm going to put parentheses around that one again, but I'm going to leave some space after the 0 to put units in. If we put units in this thing, rise over run, our rise would be meters divided by our run of seconds. So 0.5 would mean that it's 0.5 meters for every 1 second. So this would be meters per second. Our y-intercept, being the y value when this crosses the y-axis, would be in units of meters. Okay, and that's going to be our mathematical model. Again, I just want to make sure that we're clear that on what these letters stand for. So that's what we present on our whiteboards. Now, what we're going to then summarize here is the generalizable constant velocity equation that we can use. So our math model is only for that experiment. We're going to now replace these two numbers that were only for our tumble buggy with variables, or like a word, like velocity, for instance. And now we just can use those. Now we can use that equation for anything with a constant velocity. So I'm going to try and write this directly below it and just say now we have an equation. This is an equation for constant velocity. We can apply this equation to anything moving at a constant velocity. Okay, so the idea here is we're going to have x equals what letter times t plus what letter. And so we have to then use a letter for what is 0.5 meters per second, meaning like what's a word? that represents 0.5 meters per second. What is 0.5 meters per second a measure of? And in class, we realized that if it's 0.5 meters for every 1 second, that's how far it's going each second, and therefore its velocity. Okay? And then this is going to be the y-intercept, which means the initial position, the initial location on a tape measure. So that's going to be also an x value, but we're going to put a little x naught, meaning x when nothing's happened. So I need to record this so we understand what's going on. So we said this is now the ending position, meaning this is where it ends up on the tape measure or meter stick. This is the initial or beginning position, meaning where it starts in the tape measure. That, yes, that will be 0, right? That's why it was 0 in our experiment. In a lot of cases, that will be 0. This v stands for velocity. And then obviously we said here that this is going to be the time that has gone by. Okay, so that's our constant velocity equation. I do want to make one quick point that this x with a little subscript 0 is pronounced x naught. Naught is a British term which means nothing. So this is always a tool that we can use, or I guess a labeling that we can use for a variable to represent the beginning or initial. Value. So it's always going to be the initial value for that variable. So for example, we could have t naught as initial time. If we had a changing velocity, we could say that v naught would be initial velocity, and etc. Okay. The last thing I want to make sure we're good on, should be a review of algebra, is this idea of delta. So this triangle is called delta, and what this means is change in, and then you'd usually put something else after this, like delta x would be change in position, right? So let's use that as an example, because that's why we're doing this right now. So if we wanted to use delta x, that would be a change in x, meaning change in position. For example, we would have them change in position that we could find using this relationship. We would, to get the change in position, we would be taking the ending location minus where you started. So for example, if you started at a 1 meter mark and walked to 5 meter mark, you went 4 meters. So in your head, you just did 5 minus 1, right? So this is how we can get what we would call distance or displacement. So delta x may be something that we want to use. Instead of ending and beginning position, we can just take the difference between the two and just say how far we want, meaning distance. Okay? So we're going to take this idea, and now we're going to blend these two together. Okay? So I'm going to combine this equation now and use delta x instead. So I'm going to rewrite this equation so you can see how I'm doing this. I subtract x naught from both sides. Then I'm left with x minus x naught is equal to v times t. This is going to be delta x. So the final form of our constant velocity equation I want to box and put in our toolbox tomorrow, which I'll explain more about what toolbox is. It's going to be an equation sheet that I'll give you tomorrow. This would go into our toolbox. That's going to be basically the same thing as what we were familiar with from Algebra 1 as the rate equation, just different letters. So if you are familiar with that, you can write that right below there. Thanks, guys.